All right, let's take a look at the questions from exam number one. So first question here, we have a table that shows military spending between 2000 and 2012. And we're asked to, first of all, find the average rate of change between the years 2006 and 2012. So how do we calculate average rate of change? So this is essentially no different than our slope calculation. So what's our change in y values? So C of 12 minus C of 6 over our change in t values over 12 minus 6. And I can read these y values or the c values directly from the table. So I get 1750 minus 1450 all over 6. So 300 over 6, that's equal to 50. So 50 what? So C is expressed in billions of dollars. So this is going to be, so I've found the number 50. So that's our numerical answer. Now we want to try to interpret that. So that is $50 billion. So $50 billion. But basically we found this as a average rate of change. This is C is measured in 50 billion, or sorry, C is measured in billions of dollars, and T is measured in some kind of time. So it should be years. So in units, we have $50 billion per year. So basically what this is saying is between 2006 and 2012, military and arms trade spending increased on average at a rate of $50 billion per year over this time. All right, question two. So we have another table that shows us from 2008 to 2013, what is the offshore production in millions of barrels? So we're asked for what the, like, kind of how the 2-year average rates change happen here. So basically, how many different 2-year intervals am I going to have? Let's just keep note of all of them first. So 0, 2, 1, 3, 2, 4, and 3, 5. So if I'm looking at 2-year spans, those are all the 2-year spans I think I can come up with based on the information I have. So for all of these, I can find an average rate of change. So average rate of change is going to be equal to, what's it called? S. So S of 2 minus S of 0. These are all going to be over 2. I'm looking at 2-year averages. So what is S of 2? 1.94 minus 2.25 over 2. I wrote down some of these numbers in advance. So this comes out to be negative negative 0.155. So all of these calculations can basically do the same thing, all the same way. I'll do one more kind of long form here. S of 3 minus S of 1, also over 2. And we get 1.90 minus 2.01 over 2, which all told comes out to be negative 0.055. The other three I'll just write down. So basically, these calculations are all done the same way. What you're changing from calculation to calculation is what your intervals are, like what are the endpoints of the interval you're looking at. So our next rate of change comes out to be negative 0.02. And finally, this comes out to be 0. All right. So all these are all different 2-year average rates of change. So what's happening here? Basically, what this says is that over this time period from 2008 to 2013, we're seeing that the average rate of, the average rate of oil production by Pemex is decreasing, but it's decreasing until it comes to, till it comes to a behavior where it's not changing at all. So if you look at our table again, we're seeing that these last 3 years, they all have the same level of production, which is why we see an average rate of change of 0 across that time span. All right, moving on to question 3. So I have the air temperature on this point on the planet Venus is given by this function. So what was the temperature at 8 p.m. and how fast was it changing? So we have a couple different questions there. First, what was the temperature at 8 p.m.? So let's be careful here. This function basically has a reference time. Our reference time is 5 p.m. So if I care about what's happening at 8 p.m., then I need to evaluate this function at 3. So f of 3 equals 880 plus 2 times 3 squared minus 20 times 3. And for some reason, I didn't write this down. So let me calculate this real quick. So 880 plus 18 minus 60. So we get a number there of 838 degrees Fahrenheit. So at this point in time, the temperature at this location is 838 degrees Fahrenheit. So I also want to know how fast the temperature was changing. So how do I find out how fast something's changing? That is where I need the derivative. So I'm going to look at f prime of 3. You're also asked to use the limit definition. So I'm going to set that up now. So how do I find the limit definition of derivative? So the limit as h approaches 0 of f of 3 plus h minus f of 3 all over h. I realize you could do that. I mean, you have all been using the power rule for weeks now, so you can use that as a good way to check your answer. But for this question, we are looking for this limit definition, so I'll kind of work with that now. So if f of t is equal to this here, then what is f of 3 plus h? So now let's start filling in the details. So 880 plus 2 times 3 plus h squared minus 20 times 3 plus h minus f of 3. We found f of 3 a little bit ago. That's 838. This is all over h. So we can't evaluate this limit yet, but hopefully when we do some algebra here, we can get to a place where we can. So let's start combining some terms. What is 800 minus 838? I believe that's 42. So 42 plus 2 times 9 plus 6h plus h squared minus 20 times 3 is 60. Minus 20h. And I already dealt with the 838. So I still don't see a way to deal with this limit. So let's keep simplifying. So 42 plus 18 plus 12h plus 2h squared minus 60 minus 20h all over h. Now it looks like all my constants. I have 42 plus 18, which is 60, which I'll cancel out that negative 60. So now what do I have? I have the limit as h approaches 0 of 12h minus 20h, that's negative 8h, plus 2h squared all over h. Let's factor out an h from the numerator. So negative 8 plus 2h all over h. Now these cancel. So now I'm at a point where I can actually evaluate this by plugging in 0 to the remaining location of h. And what do I get? That's negative 8. So that's what the derivative is. We're also told to interpret our answer in the context of the situation. What does that mean here? So that negative 8, that's the numerical answer. But what does that mean? It means that the air temperature near Maxwell Montes on this planet, on the planet Venus, is doing what? It is decreasing at a rate of 8 what? So the temperature is given in degrees Fahrenheit. So it's decreasing at a rate of 8 degrees Fahrenheit, but a rate implies that I have two different quantities that are changing together. What's the other quantity here? It's per some unit time, which is measured in this case in hours. So basically, at this time, the temperature is 838 degrees Fahrenheit, but it's decreasing at this instantaneous rate of 8 degrees Fahrenheit per hour. So moving on to question 4. All right, so this function gives basically oil imports from the US to Mexico over this 4-year span. So first thing I want to do is this, find DIDT. So how do I find DIDT? I'm not told to use the power, or sorry, not told to use the limit definition. We have a polynomial, we can go straight to use the power rule. So what's the derivative of negative 39t squared? That'll be negative 39 times 2, which is negative 78. Reduce the power on t by 1, so that's t to the first. And the derivative of 800t is 800. So DIDT equals negative 78t plus 800. So that's the first thing I was asked to find, is this expression, this derivative. Determine at what rate oil imports were changing at the start of 2012. So T is the number of years since the start of 2000. So that means I want to evaluate this at T equals 12 years after 2000. So that's equal to negative 78 times 12 plus 800. And did I write that down? Yep, we got a value of negative 136. So basically the oil production or oil import at this time is decreasing at an instantaneous rate of 136,000. Let me just do this. So it's decreasing by 136,000. Was it 1,000? Yeah, well, that's right. I got 1,000 barrels per year. All right, question 5. Okay, so the median home price given by this function over this period of time. T is the number of years since 2010. So first thing I'm asked to do is to find P prime of T. P prime of T is equal to, I can use power rule again. 4.5 times 2 is 9. Reduce the power on T by 1. Derivative of negative 15t is minus 15. So here's my derivative. I'm also asked to find P prime of 1. P prime of 1 is equal to 9 minus 15, which is negative 6. So what does this answer, negative 6, tell me about home prices? So in 2010, no, not 2010, in 2011, I should be even more specific, in January 2011, home prices are decreasing at a rate of, is it $6 per year? No, $6,000. So $6,000 per year. And question number 6. So the cost in thousands of dollars of airing end television commercials during the Super Bowl is given by this function. So first, find the marginal cost function. So this is a total cost function. How do I find marginal cost? I take a derivative of that total cost function. So this derivative of 20 is 0. Derivative of 4,000n is 4,000. And what's the derivative of 0.05n squared? So I want to multiply 0.05 times 2, that's 0.1 times n. So that's the marginal cost function. Now I want to use that to estimate how fast the cost is increasing when I air 4 commercials. So C prime of 4 is equal to what? 4,000 plus 0.1 times 4, which is equal to 4,000.4. Is it $4,000 and change to run a commercial? No, this function gives me my answers in thousands of dollars. So this is actually what? 4,400,000. So that's what the marginal cost is. So it's an estimate that the fifth commercial will cost me $4,400,000. So I want to compare that with the exact cost of that commercial. So to get that, this function only gives me the total cost of airing commercials. So what's the cost of airing 5 commercials? What's the cost of airing 4 commercials? And then I will find the difference there. So if I plug in 5 to C, actually, I don't think I wrote down the individual numbers. So let's go ahead and do it now. So let's just do this one at a time. C5 is equal to 20 plus 4,000 times 5 plus 0.05 times 5 squared. So 20 plus 20,000 plus 25 times 0.05. That's 0.125, I believe. So what do we get? 20,000, 20.125. And then C of 4 is equal to 20 plus 4,000 times 4 plus 0.05 times 4 squared. So 20 plus 16,000 plus 16 times 0.05, which is 0.8. So that comes out to be 16,020.8. So what's the difference there? So C of 5 minus C of 4 is equal to what? 20,020.125 minus 16,020.8. So I get $3,999, and I'll even give it to you as accurately as it gives to me. So this value here. So, but remember, I got to give that in. This gives it to me in thousands of dollars. So the exact cost of running that fifth commercial is going to be $3,999,325. All right, moving on. Question 7. So the total spent on research and development by the federal government between 2002 and 2012 is modeled by this function. What was the total spent in 2010 and how fast was it changing? So 2 different questions there. First, I want to find out what the total we spent in 2010 was. So this function gives the total cost. I'm going to evaluate this function rather than its derivative. So what is S of, what value of T do I want? T is the number of years since 2002. I care about how much was spent 8 years after that, so I want S of 8. S of 8 is equal to 29 times the natural log of 286 times 8 plus 2860. And the value I got for that was 247.84. What does that mean in the context of the problem here? This is in billions of dollars. So in 2010, we spent $247.84 billion. Okay. The other part of the question is how fast is it changing? So in order to figure that out, I have to take a derivative of this function. So S prime of T equals what? 29 is a multiple. It's a constant multiple. So basically, I'm just going to carry it with me. How do I find the derivative of a natural log? So we're going to have to use the natural log rule and the chain rule here. So let's think about this in 2 different ways. Kind of the outer layer here, the outer function here is the natural log of something. So what is the derivative of a natural log? The derivative of a natural log is 1 over basically whatever you're taking a natural log of. So 1 over 286t plus 2860. So that's the outer layer of the chain rule there. What does the inner layer tell us to do? Now I want to multiply that by the derivative of the inside function, which in this case is going to be 286. So our derivative is 29 times 286 over 286t plus 2860. So to answer this question about the rate of change, I'm going to evaluate the derivative at 8, and I get this value, 1.611. So what does that mean? That means that in 2010, we are spending $247.84 billion on research and development, and that spending is increasing at this instantaneous rate of $1.611 billion per year. And finally, question 8. The price P that a bookstore charges for its latest edition of the current bestseller is related to the demand Q in weekly sales. So if the price is set at $40, compute the rate at which demand is changing with respect to price. So we're asked to give a rate here, but we have to be specific about what that rate is. That rate is the rate at which demand is changing with respect to price. So what is the variable that talks about demand? That's Q in this case. So I want to find dQ with respect to price. So the variable that talks about price is P. So I want to find dQ dP here. So here's my equation, and we're going to have to use some implicit differentiation here. 100 PQ plus Q squared equals 5 million. And what I'm going to do here is I'm going to differentiate both sides of this equation with respect to P. Let's just go term by term. 100 PQ. So I kind of have to treat P and Q as if they're both variable functions. So because of that, I have to use the product rule. So let's do this. Let's pull out the 100 and treat this like a constant multiple. Now we're taking the derivative of PQ. And how does the product rule say we do that? So I do the derivative of the first function, which is 1, times the second function, as is, that's Q, plus the first function, which is P, times the derivative of the second function. So that's going to be dQ dP. So that's the product rule. Now what's the derivative of Q squared? So that's going to be, got to use the chain rule there. So our outer function is basically, I'm squaring something. So how do what's the derivative of squaring something? Well, it's 2 times whatever that something is. But now I got to multiply that by the derivative of Q with respect to P. So that's going to be dQ dP. So that should handle the left-hand side of our equal sign. What happened on the right-hand side? We have the derivative with respect to P of 5 million. 5 million is a constant, so its derivative is 0. So now let's start cleaning some of these things up. So I get 100Q plus 100 P dQ dP plus 2Q dQ dP equals 0. So let's remind ourselves, what were we asked to figure out here? Compute the rate at which demand is changing with respect to price. So I want to find an expression for dQ dP, and I think we can assume that P is $40, so we can go ahead and set that now. So 100Q plus 100 times 40, so 4,000 dQ dP plus 2Q dQ dP equals 0. So we're getting closer. To start trying to isolate dQ dP, I'm going to get everything that doesn't have that dQ dP, that derivative term, on the other side of the equal sign. So 4,000 dq dp plus 2q dq dp equals negative 100q. Next, I'm going to factor out the dq dp from everything on the left-hand side. So 4,000 plus 2q equals negative 100q. Now I'm going to divide both sides by this 4,000 plus 2q quantity. So dq dp equals negative 100q over 4,000 plus 2q. And that is our expression. That's our derivative. So we're also asked to interpret that result. So basically, we don't have a number here because we were not given a condition for, what the demand was at a certain time. But basically, this expression here, dq dp, is equal to this expression. So kind of qualitatively, we can say here that as the demand goes up, so if we let Q increase, basically the demand is going to go down. But yeah, that's our expression, and that should do it for exam number 1.